Hello, welcome to yet another video of Cornerstones of Math, and welcome to yet another sequences and recurrence relation videos. So far we have covered some of the most basic types of recurrence relations. Now let's move on to something more complicated. If you take a look at given problems here, you might think that these recurrence relations suddenly got crazier, but they are not as complicated as they seem. With one simple trick, we can convert these into more familiar types of sequences. And that trick is called substitution. For example, for the first one, let us divide both sides with n plus 1. Then we have an plus 1 divided by n plus 1 equals an divided by n plus 4. Here, let us use substitution to simplify the recurrence relation a little bit. Specifically, let new sequence be n as an over n. Then this an plus 1 over n plus 1 is bn plus 1. So we have bn plus 1 equals bn plus 4. And this is the recurrence relation of one of the most basic sequences. This relation means that the difference bn plus 1 minus bn remains 4, which is constant. Therefore, sequence Bn is an arithmetic progression with a common difference d equals 4. Here, the formula for the nth term of the arithmetic progression is first term b1 plus, adding up the common difference d, n minus 1 times. So we have b1 plus n minus 1d. And here, b1 is a1 divided by 1, and since a1 is 1, b1 is also 1. So we have bn equals first term 1 plus common difference 4 times n minus 1, which is 4n minus 3. This means that an divided by n equals 4n minus 3, which means that an equals 4n squared minus 3n. And this is the answer. Next, we have this three-term recurrence relation that looks nuts, but this one too is not that difficult once you know the trick. It may be not easy to figure out at first glance, but what we need to do is to divide both sides with an plus 1. That gives an plus 2 over an plus 1 equals an plus 1 over an plus 1. So now we can use the substitution again. This time we let bn as an plus 1 over an. Then we have bn plus 1 equals bn plus 1. So here we have the recurrence relation of the arithmetic progression again. Specifically, sequence bn is an arithmetic progression with a common difference d equals 1. So let us apply the formula for the general term of the arithmetic progression again. And here, b1 equals a2 over a1, which is 1 over 1, which is 1. So we have bn equals 1 plus 1 times n minus 1, which is just n. This means that an plus 1 over an equals n. Therefore, an plus 1 equals n times an. And I have already covered this type of recurrence relations in my previous recurrence relation video. This is the type where you have to substitute n with 1, 2, 3 all the way up to n minus 1 and multiply them all. That is, first we have a2 equals 1 times a1, then a3 equals 2 times a2, a4 equals 3 times a3, and so on, and an equals n minus 1 times an minus 1. So multiplying them all, we have terms cancelled out, and we obtain an equals a1 times 1 times 2 times 3 times so on, times n minus 1. And since a1 equals 1, we simply have an equals n minus 1 factorial. And now we have arrived at some of the most famous types of recurrence relations where we rearrange terms to use substitution. The all-time famous an plus 1 equals pan plus q form. Here the pro tip is, for the recurrence relation an plus 1 equals pan plus q, convert it into an plus 1 minus alpha equals p times an minus alpha. So for our specific problem, let us find alpha satisfying an plus 1 minus alpha equals 3 times an minus alpha. This means that an plus 1 minus alpha equals 3an minus 3 alpha. So we have an plus 1 equals 3an minus 2 alpha. If we compare this to the given relation an plus 1 equals 3an minus 4, we know that alpha equals 2. Therefore, we can write the given recurrence relation as an plus 1 minus 2 equals 3an minus 2. So letting bn as an minus 2, we have bn plus 1 equals 3bn. So we have the recurrence relation of another very basic sequence, the geometric progression. Here, sequence bn is a geometric progression with common ratio r equals 3. The nth term of the geometric progression can be obtained by bn equals first term b1 times common ratio r to the power of n minus 1. And in our problem, b1 is given as a1 minus 2, which is 1 minus 2, which is minus 1. Therefore, bn equals first term minus 1 times common ratio 3 to the power of n minus 1, which can be written as minus 3 to the power of n minus 1. This means that an minus 2 equals minus 3 to the power of n minus 1, which means that an equals 2 minus 3 to the power of n minus 1. And that was all for today's video. For my next recurrence relation video, I actually plan to show you much more complicated recurrence relation, so if you don't want to miss it, please subscribe to my channel, and as always, I will see you in another video.